Okay, so we're going to look at the second part of our look at problems involving elastic energy. Mainly, I think I want to use this session for you to just have some practice of a few more questions, but we'll run through a couple of examples in any case just to get you back in the swing of things. This first thing I have on the try now is something I've just made up, which I think is a good precursor to a question that you'll see in the textbook, where you have to use a little bit of geometry to answer the question. So in this case, you've got my attempt to draw a bow and arrow. It consists of a vertical rod, which is 1 meter long, and a hand pulling back on an elastic bowstring. And as you can see, I've stated the details there. The bowstring, when it's not stretched, it just is attached to each end of that 1 meter rod and is naturally at that length. So it's then stretched back. It makes an angle of 30 degrees at the top and bottom, and it's then released, and this 300-gram arrow is then fired at 40 meters per second. The question then is, what is the modulus of elasticity of the bowstring? So to answer this, make use of the elastic potential energy formula. So note that one down, and then have a think about, the extension of the string, the geometry of the situation. Mark on some lengths first, and then see if you can answer the question using energy considerations. So give this one a go before I give you the answer. You can pause the video now. Right, so to begin answering this, we've got the 1 meter rod, and hopefully you will then have considered what the length of the bowstring is as it's being pulled back by this hand. So you've got 30 degrees there on that angle, that's 30, and therefore if we take this as two triangles, so that triangle there will have a length of a half. So if we then want the hypotenuse, we're going to use cos. So the hypotenuse is the adjacent divided by cos theta, isn't it? So if we take a half and divide that by cos of theta, or cos of 30 in this case, which is a half over root 3 over 2, which then gives me 1 over root 3. That tells me the length of one part of that bowstring, right? But the full bowstring is going to be double that, right? So the bowstring length is currently 2 over root 3. However, its natural length is 1. So that means the extension is going to be 2 over root 3 and then minus 1. Right. Just as a sanity check, let's double check that 2 over root 3 is actually bigger than 1, which it must be if we've done some calculations correctly. It's about 1.15. So if I take away 1, just so we'll note it down, but I'll use the third form in the calculation. That's about 0.155. Okay, and then we've got the extension. So let's over here work out the elastic potential energy currently stored in that bowstring. It's going to be lambda x squared over 2L. In this case, L is 1. Lambda we don't know yet, we want to find it. The extension is 0.155. In fact, I did say I was going to keep the third form, but actually I don't think it's worth it. It'll get a bit too complicated. So let's use the decimal form, but be a bit more specific. 0.1547 is a bit more accurate. So then we'll put that in there. We'll get 0.1547 squared, which, oh, that comes up quite nicely actually. It's just, oh no, it doesn't. My mistake. Hang on. No, I squared the wrong thing. It doesn't come out nice at all. It's about 0.02393. Let's just divide that by 2 straight away actually. to save on rewriting lots of decimals. So you should get, or you should have got, 0.01197 rounded lots of lambda. Okay, so that's the elastic potential energy, that number times lambda. Okay, so let me just make some space for working. So is that the only energy that we've got going on in the system? Technically the arrow has some gravitational potential energy, but we're only going to be considering the horizontal or the situation that's going on horizontally. The gravitational potential energy doesn't really come into this because the initial speed is 40 meters per second, and then of course straight away it's going to start going down to the earth, this arrow, but initially there is no vertical change, so we don't have to worry about GPE. So we've got EPE and the initial kinetic is 0. So therefore that elastic potential energy, once the bow has reset back to its natural length, is going to be fully converted to kinetic energy. The kinetic energy of that bow is going to be a half times its mass, 0.3 times 40 squared. In this case, that comes to 240. So finally, we have lambda must be equal to 240 divided by 0.01197, and the answer then is a pretty big number. It's roughly, I'm going to round quite a bit, it's roughly 20,000. Okay, so what that large number is telling you is effectively that for something like a bow and arrow, you need a really stiff elastic string. I suppose it doesn't really feel that stiff if you ever used a bow and arrow, but it does take quite a bit of effort to pull it back, quite a bit of work. It's not elastic like an elastic band is elastic. It needs to be a lot more stiff than that. So that way you require a lot of work to pull it back, but therefore you transfer a lot of energy into elastic potential. You then let go and it's released into a large amount of kinetic energy in this case. Okay, so that's it. That's our lambda. It's 20,000, roughly. Okay, so I'd like to do one more example, the last one in the textbook, before giving you some more questions to do. In this question, we're going to make full use, I don't think we've done this yet, of absolutely every component in that conservation of energy equation that we've slowly built up. If you remember, it started really simple before. It was change in kinetic plus change in potential is constant. And now we've got the full version, which I'm going to write again, is change in kinetic plus change in, I'm going to start calling it GPE actually, to be more specific. That's gravitational potential energy. I think it probably is a good habit. So those two types of potential energy, those three changes added up are equal to work in minus work out. Okay, and the reason you're going to be using work in and work out, remember, work out tends to be caused by things like friction, which are transferring energy out of the system, and work in tends to be caused by things like motors or driving forces or hands pushing things, generally forces being applied over a distance, which are other than gravity or the tension from an elastic string. So what's the situation? We've got a light elastic spring, natural length 0.5, modulus of elasticity 10. One end is attached to a point A on a rough horizontal plane. Let's draw our plane, which is rough. The point A is here. And the other end is attached to a particle P of mass 0.8 kilograms. Let's just note the mass then, 0.8. The coefficient of friction is 0.4. The particle P initially lies on the plane with AP equals 0.5. Okay, so there's P, which means the spring is at its natural length, so that keeps things nice and easy. It's at 0.5 already. And then it's projected away with speed 2 meters per second. Okay, so similar to a previous question, that speed has nothing to do with the spring itself. It's presumably caused by someone holding the particle and giving it a bit of a push. And now it's going at 2 meters per second initially. Because of course the spring is neither compressed nor stretched at this point. So that speed is being caused by something else. Effectively, it's just an initial condition, its initial state. And it's projected to the right away from A. Find the distance moved by P before it comes to rest. So what is this distance? What should we call it? I think we can call it X actually. X would be an appropriate name for it, because it does correspond to the extension of the spring in this case at that point, right? That won't always be the case, in which case you might want to call it something else like H or D or something, but in this case it corresponds to the same thing. So at that point, whatever it may be, it's at 0 meters per second. So we've got our before and after scenario effectively, right? So this is our initial situation, and this is our final position. All right, there and there. Okay, so we want to label some forces in this case. The weight is in this case 0.8 g. It's not falling through the floor, it's not flying up in the air, so therefore the reaction force must be the same. And we've also got the friction force, right? So in this case, this object P is being pushed to the right, so there's going to be friction going to the left. And that friction is going to be mu times the reaction, which is 0.8 g. So we're going to have 0.4 times 0.8 g, that's 0.32 g. Okay, so those are all the forces. You've got the weight, the reaction, the friction. I think that's everything we need. So let's work out these various components now, the changes in these various types of energy. So kinetic energy is always the easiest, I find. It starts at a velocity of 2, ends at a velocity of 0, so it ends at 0 kinetic energy. So its change is going to be negative. Let's write it here. The kinetic energy, the change in it, is going to be negative half mv squared. In this case, that's a half m 0.4 times 2 squared. So 0.4 times 4. So we're going to have 1.6, negative 1.6. That's our decrease in kinetic energy. Gravitational potential energy, in this case, won't change. So I did say we were going to use all the components. Actually, it turns out we're not using GPE in this case. We will be using work in a moment though. So GPE is 0 because the object is not increasing or decreasing in height. And then the elastic potential energy, well, let's see. So it starts with no elastic potential energy at all, because the spring is initially at natural length, and then this spring, when it gets to this point over here where it's 0 speed, will have extended by x being this unknown, right? So that's why we chose x, right, as the letter, because it coincides with the extension. So the extension is x, so we're going to do lambda x squared all over 2L, which in this scenario gives us 10x squared divided by 2 times 1. No, sorry, 2 times 0.5, which is 1, and that's 10x squared. So whatever x is, 10x squared is the elastic potential energy, and that is a positive number because you've gone from 0 to 10x squared. So then the next thing is this win, well, this win and wow, the W in, W out. No energy has been added to the system, so W in is 0. I'm just going to write that here. And then W out, so energy lost to the system, or from the system, is caused by that friction. So that friction force is being, the object, this P on the spring, is working against that friction in some sense. So that means some energy is lost from the system. That's going to be the friction force times the distance over which it acts. So that friction force is 0.32 g, and it's going to act throughout the motion where it travels this distance x, right? Effectively, work done is force times distance, right? So work done against friction is 0.32 g times x. Okay, so we'll just write 0.32 gx. So that allows us, going a bit all over the place on this one, let's go over here. That allows us to create our final equation, right? So we're going to have minus 1.6. We'll ignore the 0, plus 10x squared, and that's going to be equal to work out, which we're taking away, so it's minus 0.32 gx. So we end up with our final equation, which is, let's write it as a full quadratic, 10x squared, in this case, plus 0.32 g x minus 1.6 equals 0. Okay, so we've got it. We've got a quadratic. We solve it. Use whichever method you like. Complete the square, or probably more likely calculator. x1 equals x2 equals. In this case, I'm just going to check them from the book. It should be one of them as 0.2728, and the other will be minus 0.586. Okay, so we get two solutions. That doesn't mean that there actually are two solutions. Remember, throughout this process, we're starting with mathematical truths, and the result is x could be this, or it could be this. It's at least one of them. Sometimes it's both. It depends on the situation. But in this case, we know that x is not going to be negative. It's not going to be 0 the first time when it's been pushed to the left. So we ignore our negative solution, and our final answer is this one here. It's 0.2728. Yeah. Okay, and that's our value for x. That's the distance at which this object first comes to rest. And in fact, in this case, this is also answering the question, what is the maximum displacement to the right? Because if it reaches a velocity of 0, we know that that's the point at which it's going to start coming back in the other direction, right? Cool. All right, so that example done. I'm going to leave the rest of the time for you to try some questions now, so I'll put some up for you to try. So I've got 4 questions total. That should be plenty to get on with. 3 standard, slightly harder within this topic, exam style ones, and the 4th question is a challenge one. So if you have time for it, you can give it a go. Be impressive if you can do all 4 in the time you've got. So this is the first one. You can pause the video and give this one a go. Okay, and now have a go at these 2. Note that in question 8 you need to use coefficient of friction. Throughout all of these, I would suggest using the KE plus change in GPE plus change in EPE equals W in minus W out. Particularly for number 8, because you've got friction going on there as well. So give these two a go. You can pause the video now. And then if you've got time and you want to be impressive, have a go at this challenge question as well. Quite a bit of algebra going on in this one. See how you do. Pause the video now.